Anode mud obtained during electro-refining of copper contains which of the following combinations? Anode mud. It is the product that is obtained during electrolytic refining of copper. After obtaining copper, we are not sure whether copper is 100% sure, 100% pure. We get what is known as blister copper. To get 100% pure copper, we use electrolytic refining of copper methodology, in which impure copper is made as anode. Pure copper is deposited on cathode. The impurities settle down as anode mud. But what is the combination of this anode mud? Anode mud contains gold and silver. How is it possible? What guarantee that we give to relatively tell that copper contains gold and silver? Because of the relative closeness that it has in the electrochemical series. It is present below hydrogen in the electrochemical series, and all these will be in the form of pairs or triplets. Copper will usually be associated with very minute particles of silver as well as gold. Therefore, the right option for this happens to be option D, that is silver and gold. Extraction of zinc from zinc blende is achieved by, I remember discussing this little while ago, zinc blende, ZNS, because it contains sulfide. After concentration, you are doing roasting. On roasting, you get zinc oxide. Zinc oxide is reduced to zinc using carbon as a reducing agent. Hope you have understood. Sir, zinc blende, concentrated because sulfide is there, concentrated by froth flotation process. Because sulfide is there, again we do roasting. On roasting, we get zinc oxide. Zinc oxide is reduced to zinc using carbon as a reducing agent. Keeping this statement, find out which is the right option. Electrolytic refining, ruled out. Roasting followed by reduction with carbon, most appropriate. Therefore, option B is the right answer. Let us look into the others. Roasting followed by reduction with another metal. First part is right, but the concluding part is not right. Therefore, I go for the option B, roasting followed by reduction with carbon. Hope you have understood this, my dear students. From all these questions that we have learned, if you could understand the basic terminologies in this chapter, if you could know the combinations of the ores, the alloys, the concentration methodologies, principles employed, examples for each of the techniques that you are doing, you will be successful in doing better in this chapter. We'll move on to the next question. As we have discussed a couple of questions on concentration of the ore, reduction, let us concentrate on refining techniques, which earlier we have again done this. Repeatedly, we are doing the same questions. Zirconium and titanium is refined by, I would like to tell, refining is a final stage of getting the metal in 100% pure state. We have done. Nickel is refined by Mons process. Zone refining is used to get ultra pure metals. In this I have zirconium and titanium. Mond's process ruled out. Let us look into distillation. Distillation is employed for those metals which are volatile in nature, such as zinc and mercury. Liquation is employed for refining those type of metals whose temperature, whose melting temperature is lower than that of its impurity. Van Arkel process is used for refining zirconium and titanium. If I happen to look into these, I would like to summarize and then tell. Mond's process specifically used for refining nickel. Zirconium and titanium is refined by Van Arkel methodology. Liquation is used to refine those metals whose melting temperature is lower than that of its impurity, example bismuth and lead. Distillation is employed for refining metals which are volatile in nature, such as mercury. The right option for this is zirconium and titanium is refined by Van Arkel method. We have discussed a couple of questions on concentration, reduction and refining. Let's move on to another, Ellingham's diagram. Let's discuss in detail about Ellingham's diagram. Ellingham's diagram is a graph of standard free energy change versus temperature. Ellingham's diagram is used to select the best and the most suitable reducing agent for the reduction of metal oxides into metal. Using Ellingham's diagram, we come to know that it is not only carbon which acts as a reducing agent, but plentiful metals which act as a reducing agent depending upon the nature of the metal oxide. Some of the salient features of my Ellingham's diagram is, as I mentioned, Ellingham's diagram is a graph of standard free energy versus temperature. Greater the negative value of delta G naught, greater is the reducing capacity of that element. Greater the negative value of delta G naught, greater is the reducing capacity of the element. In Ellingham's diagram, as we draw the graph for it, the graph would show sloping upwards. If you tend to take the slope of the line would indicate and refer that at a particular point where there is a change in the slope of the line, the particular point wherever there is a change in the slope of the line, it undergoes transformation. Meaning, all this while it was a liquid tends to become a gas. All this while it was a solid tend to become a gas. Therefore, wherever there is a change in the slope of the line, it undergoes phase transformation. Keeping these points, let's try to answer this question. In Ellingham's diagram, I have given all the options here. So, better we know about Ellingham's diagram.